Guess
Sorry, I had.
Trig has all kinds of levels of difficulty.
That's right.
This is definitely a level that I have not encountered recently.
Okay.
But I think I can probably do most of these. I
Okay.
haven't really had enough time to try to do them yet. I've tried to do a couple of them. But
Yes, sir. Sorry about that. I had trouble sending it with.
no problem. It might even be more helpful to you if we sit and try to figure out how to do these together,
All right.
rather than me automatically knowing how to do them. Let's start with one, I guess. I don't know. Do you want to start with
That's
one?
that sounds good.
Okay. And let's see if I can figure out how to do this. The software seems to have improved significantly here so that I can close this method out easily, which I haven't been able to do in the past. So I can write and erase. So let me start up here. First of all, one of the secrets to solving these trig equations is to try to get everything into the same trig function. You know,
Yes, sir.
if I have sine equals cosine, that's hard to solve. I mean, that specifically isn't hard to solve, but that's the what we're going to try to do here.
Yes, sir.
Okay, so let's secant is 1 over cosine, tangent is sine over cosine. Seems to make sense to do that.
Yes, sir. Okay.
In other words, to use those particular identities because they both introduce cosine.
All right.
Now, let's treat that as an algebraic equation. How can I get rid of denominators?
We would just multiply it all by cosine of x.
Okay.
Or
Yep.
wait. Yes.
No, that's exactly right. This becomes cosine squared. Okay. Now, the Pythagorean identity for cosine squared is what?
I don't think I've heard it be called that. What is that?
It's the sine squared plus cosine squared equals 1.
Yes.
That's the Pythagorean identity. And then there's
Okay.
a couple of others also. There's tangent squared plus 1 equals secant squared. There's 3 of them. All your basic trig identities, you want to be really good.
Yes, sir.
These are going to be impossible to do if you don't know those. But
1 plus tangent.
yeah,
1. Yeah.
if I use 1 minus sine squared in place of cosine squared, in other words, I'm going to do this. That's the identity for cosine squared. And the reason I'm doing that is because now I have everything in sine x, and it's really a quadratic. So if I distribute, I get 2 minus 2 sine squared x plus sine x equals 1. Now if I move everything in the quadratic over to the other side, I get 0 equals 2 sine squared x minus sine x minus 1. Follow all of that?
Yes, sir.
Okay, now what we're looking at the bottom, you can think of as a quadratic. It is in fact called a quadratic in sine x because the middle term is sine x. You can have lots of quadratics. You can have quadratic in x, which would be standard x squared, so forth. You can have quadratic in e to the x, where your middle term is e to the x and your first term is e to the 2x. As long as the first term is the square of the middle term, you can make it a quadratic.
Yes, sir.
Okay, so how do I solve that?
All right, so that's going to be 2 sine x plus 1, or yeah. And then we have plus 1 minus 1.
Yeah, that works. That produces the proper quadratic. Now what?
Now we set both of those equal to 0, so we get the sine of x is equal to 1, and the sine of x is equal to negative 1/2.
What's the solution to the top one?
That is 90.
And since they have not restricted the domain, we need all of the solutions.
Okay, so that's plus 2 pi k.
That should be the answer. Oh, for the first one. And the second one?
That is 150. So is that?
No, actually, it's not 150. And in fact, if you put that into your calculator and take the inverse sine of negative 1/2, it'll give you minus 30 degrees.
Yes.
So that's a good answer. Minus pi over 6 plus what?
Plus 2 pi k.
Now,
And
let me think about that.
there's one more, right?
I think this one requires two different.
Yes.
That's one of them, but there's actually another solution that your calculator doesn't give you.
Negative 5 pi over 6.
Well, let's make it a positive angle. We don't need both negative angles. I think that angle is 2 pi over 3, isn't it? In other words, the angle where sine would be equal to negative 1/2 would be in the third quadrant.
Yes.
The reference angle would be pi over 6. So it's pi plus pi over 6, which is 4 pi over 6, which is 2 pi over 3. So 2
Wait, is it 240 or 210?
It's 210. It's where that reference angle is 30 degrees. So it's pi plus pi over 6. Oh, that's 7 pi over 6. Excuse me. That's what the answer is 7 pi over 6.
Yes.
If you put, what's the sine of 7 pi over 6 in your calculator, it'll tell you negative 1/2.
Yes, sir.
And this also, you'll notice the first one does not give us that angle. No, it doesn't. The first one merely gives you the fourth quadrant angle over and over and over again.
Yes, sir.
So you have to spell out the third quadrant solution. Here, I haven't written it very nicely here. Let me, oh shoot, I can only erase it. I don't want to do that. That's oh nice. That's a 6. Yeah, the first one, when k is 0, it's minus pi over 6. When k is 1, it's 11 pi over 6. So it never does find the 7 pi over 6 answer with just the first one. And that's pretty much always the case when you have numbers other than 1 or even 0. might have two lines in it.
Okay.
Whereas there's only one place in the unit circle where sine of x is 1, and that is at pi over 2.
Yes.
So there aren't two spots like there are where sine of x equals minus 1/2. There's two places where that's true. And in fact, this can probably be simplified into that. It's minus pi over 6 plus pi k.
Yes.
Now hold on a second.
But wait, wouldn't that just
I
make it?
think that still needs to be 2 pi.
Yes.
I was thinking that no, this is correct. Okay, next one.
Yes, sir.
You have answers
And
to these, by the way?
no, sir.
Okay. Incidentally, today we're supposed to do an hour and a half, but I'm going to have to leave 5 or 10 minutes early, if that's okay.
Yes, sir. I wanted to let you know about that. My mother just emailed you. We're only going to be able to do an hour today, as well as an hour next Thursday.
Perfect. Perfect. That way I
Okay.
don't have to cut it short. So, okay, good.
Good.
Okay, so let's do the next problem here.
Yes, sir.
And before I do, or try to do 2, on problems like 3, or even 4, are you allowed to use your calculator?
No, sir. Well, we're supposed to write out the distinct way that we solve this.
Okay, and does the answer have to be in exact radical format, or can it be in decimal? Decimal approximation.
I think it would be in radical.
Okay. Let's look at number 2.
Okay.
These are always tough because we don't have any identities that are cosine of 3x.
Okay.
Okay. So I got to do something with that, I think. Let's see. The way I would go about trying to do number 2 would be I would separate it like this.
I think I think we have a cosine 3x identity.
What is it? Hold on. Yeah.
Although I'm not sure if it would work in this case.
Well, I tell you what, let's try this, because I think this will work.
Okay.
Okay. So we're going to use the sum and difference.
All right.
What's the answer?
So that is...
And I'll start it way over here to the left because I'm going to be going horizontally. So it's, what's the sum and difference identity for this?
So that's the cosine of 2x times... all right, so for cosine, it's cosine times cosine, right? And then sine times
cosine, opposite sine sign.
Okay. So cosine 2x times cosine x minus sine of 2x sine of x.
Okay, and that's just that term right there.
Yes.
Okay, so we still got this part. All right, now
Do we want to use the cosine and sine 2x formula?
I'm not sure. I think I want to group these. Group the middle two terms and the other two terms. Let's see what happens if I do that. In other words, cosine 2x, cosine x, minus cosine x. And on the other side of the equation, we got sine of 2x, sine of x, plus sine of x. Now, notice we can do some factoring. What can I do on the left?
We can take out a cosine x.
Leaving and do the same thing on the right.
Is it 2 cosine squared x?
No. Just,
Or is that just cosine?
oh, I see I see why. I didn't write it very clearly here.
So it's cosine 2x
Yes.
minus 1, not cosine squared x.
Oh, okay. Thank you. I was making the mistake, not you.
Okay.
Yeah, you're right. It's cosine 2x. Okay, now using the double angle formula for cosine. Now let's see, what do I want to put all of that in? Let's do the right side first because there's only one double angle formula for sine of 2x.
2 sine cosine?
Yeah, let's see if that might not help us decide which identity to use on the other side. Yeah, and now we're going to end up with a sine squared. If I distribute, well, let me think for a minute. Let's see, so the right side's going to go to 2 sine squared of x cosine of x plus sine of x, right?
Yes.
So let's see. We got 3 different identities to choose from for cosine of 2x. I don't think we want to use the cosine squared minus sine squared. I think
No.
I'm going to use, let's try the one that's just sine.
Okay. That one is, let's see.
Now, does that help any? Whoops, hold on. And I got to subtract 1 from that, correct?
That's right.
Which,
So if,
I'll just take away that 1 right there. And that's what we have on the left side, I believe.
that's right. So, yeah, 1 minus 2 sine squared x, and the 1's cancel out.
So we can divide both sides by, no, we got 2 sine squared x on both sides. Let's see, what does the left side become? It becomes minus, here, I think this is going to be helpful. It becomes minus 2 sine squared x cosine x. Same thing we got on the right side.
Yes, sir.
So if I add it, to the right side, I get, I think this is going to work. Start writing in blue up top, since I ran out of room. I think we have this. 0 equals 4 sine squared x cosine x plus sine x.
Zero equals what?
What I did was I moved the left side to the right.
Okay. Yes.
Added, and so I ended up with 4 sine squared x cosine x.
Yes.
And I still have that plus sine x over there. So, now what? Let's see.
Could we divide it by sine?
Yeah. We can factor out, well, yeah, no, you're right. We can divide everything, both sides of the equation, by sine x, which gives us 4 sine x cosine x plus 1.
Wait, would that remove a solution? Would we really need to factor it out?
You're right. Absolutely. You are right. We would lose the 0 solution if it was there.
Okay.
If that was one of the solutions. I forgot. So I need to factor. So we got, no, just cosine, excuse me. So we're going to factor out. So we end up with 4 sine x cosine x plus 1.
Yes.
Divide both sides by 4. No, let's see, that's equal to 0, isn't it?
Is that?
Yeah, all of this was equal to 0, and I just divide.
Yes.
Oh, no, okay, here's, sorry. Got to do it this way. Now,
Is that 2 times the double sine formula?
the double sine formula is sine, cosine, same sign, sine, cosine. So I don't think it is.
Sine 2x. Sine 2x. Oh.
Right, sine 2x is 2 sine cosine. Good thinking. So this right here is 2 sine of 2x.
Yes.
So we've got sine of x times 2 sine of 2x plus 1 equals 0. Now we're ready to solve it.
Yes.
Our solutions are sine x equals 0, or 2 sine of 2x equals negative 1/2.
Yes.
Okay, we're going to solve it. We're going to be able to.
Okay.
Now, the top one you're good with, right?
Yes, sir.
Okay.
0 plus pi k.
Yeah, that one you can use pi, because it does repeat every pi.
Yes, sir.
You know how to do the second one?
That one, would we just use the sine 2x identity and put it back into 2? or
No,
not?
what you can do is take the inverse sine of both sides, leaving
Okay.
2x. In other words, 2x has to equal minus 30 degrees. So minus pi over 6, or 7 pi over 6, or 11 pi over 6, so forth and so on.
Yes, sir.
So x has to equal minus pi over 12, or 7 pi over 12, or 11 pi over 12, and that should be enough to find our sequence. So what is that? X is equal to minus pi over 12 plus...
So that is...
Oh, I see how you have to do this. You have to do it in two parts. Plus 2 pi k,
Yes.
or x is equal to 7 pi over 12 plus 2 pi k. In other words, those two are separated by 2 pi. This one and the next term are going to be separated by 2 pi also.
And it's still going to be 2 pi even though the angles were halved?
Yeah, I did lay out the first three terms, and it jumps by 2 pi to get from minus pi over 12 to 11 pi over 12. And it
Okay.
jumps from 2 by 2 pi, I think, or is that 1 pi? That's only 1 pi, isn't it? You're
Okay, so
right. It's not 2 pi. It's 1 pi.
okay.
Yeah, because when k is 1, my next term would be 11 pi over 12.
Okay.
Yeah. So your total solutions are
So 0 plus pi k, negative pi over 12 plus pi k, and 7 pi over 12 plus pi k.
yes, I believe that's it.
Okay.
That's all you have. So that way worked. There's probably other ways to do that problem.
Yes.
I'm pretty sure that worked.
I
Now,
think it did.
number 3. Well, I'm pretty sure I know the first step.
Okay.
It's inverse tan of 1.
Inverse tangent of 1. That is net. The inverse tangent of 1. The tangent of 1.
45 degrees. Now remember one thing about inverse tangents is you always are taking inverse tangents of numbers to find angles.
That's right.
So that's a 45 degree angle.
Over 4.
And then you have inverse tan of x equals, and that is an angle also. That's why I asked you if you could use your calculator. Let's see, what angle is that? That would be 1, 3, square root of 10. So it's that little angle right there. So the tangent of theta would be equal to 1 over 3. So that angle, I don't know how to define that. The most accurate definition is inverse tan of 1/3. Unless I want to use my calculator and come up with so there's that.
Let's try the calculator.
Well, hold on a second. I've already put this into Wolfram Alpha. I just wanted to do that before showing it to you.
Okay.
This is what Wolfram Alpha does. I got it written right, correct?
Yes.
When I first looked at this, I thought, can we take the tangent of both sides, which would leave us with 1 minus x equals 1/3, which would give you an answer of x equals 2/3. But you can't do that. If I can take the tangent of both sides. I can certainly do that. But apparently, when you take the tangent of the left side, you're not left with 1 minus x. Now, let's see what Wolfram Alpha has to say about this. The exact result is what I wrote. Pi over 4 minus tan 1, or inverse tan of x equals inverse tan of 1/3. Do realize that the inverse tan of 1/3 is a number.
Yes.
Which you could then combine with the pi over 4, which is a number.
Mm-hmm.
And you would have inverse tan equals a number.
Yes.
And then you could take the tan of both sides to figure out the answer.
Yes.
So it's definitely doable. And let me show you the rest of what Wolfram Alpha gives you. They do it by graphing it. The blue curve is minus pi over 4, excuse me, blue curve is pi over 4 minus arctan of x, the left side of that equation. In other words, it's the graph of arctan x shifted up by pi over 4. Actually, the reflection. Reflection of the arctan graph. And on the right side of the equation, they've got a horizontal line which represents the arctan of 1/3. It's a number that's about point, whatever that point is right there where my cursor is pointing at.
Okay.
That's the arctan of 1/3. It's a number, but it looks like it's an irrational number. So the answer to this equation is where those two things intersect. And that is, it looks like exactly 0.5. However, here, let me scroll down, and that's not the answer it gives. In fact, it does not give you an answer. On the number line, I can't tell. That looks awfully close to 0.5. In fact, probably is 0.5. Why they don't give that as an answer, I don't know. The other solution is x equals the cotan of all of that. And again, arctan of 1/3 is a number. And then you can take the cotangent of pi over 4 plus that number.
Yes.
So there's a couple ways to do this. I suppose a calculator would probably be needed no matter what you do. I don't see any way. They don't certainly give an exact answer here. They do. The exact result is this point where those two sides intersect. And there's a lot of problems where you kind of need to do it like that. You know, if I said to you sine of 2x equals cosine of x, how would you solve that? Well, you could graph the sine of 2x, you could graph the cosine of x, and wherever they cross, that's the answer. So if they allow you to use your calculator here, I don't know if I don't know if there is a radical exact answer here. I don't think there is. First of all, inverse or arctangent of 1/3 is a number, but it's not a, you know, pi over 6 type number. It's the only way I know to get it is to look it up in a table or go to a calculator.
Yes. I think so.
So this
So do we want
is the
to?
way
Do
to
we want to try to?
what's
Do you want
that?
me to try to? Do you want me to try to enter it in on my calculator?
It's not really going to help because your calculator is going to give you a decimal approximation.
Hmm.
As it will give you pi over 4, it'll give you a decimal approximation also. So
Okay.
then, I mean, we could certainly, sure, let's move the arctan of x to the right. Let's move the arctan of 1/3 to the left. Here, let me write it in here. And we'll have you come up with an answer that should be close to 0.5. In other words, this is what I'm suggesting. Pi over 4 minus inverse tan of 1/3 is going to equal the tan, or excuse me, the inverse tan of x. So turn that into a number.
Okay.
Make sure your calculator's in radians. You don't want to be in degrees. Because the second part of the left side would be in degrees. So what number are you left with on the left side of the equation?
0.5 exactly. Oh, wait. I solved it.
I don't think so, yeah.
Hold on. I plugged it all in as the tangent of x. Let me just solve it for the left. Let me just do the left
Just
side.
come up with a number for pi over 4 and a number for inverse tan of 1/3 and subtract those two numbers.
0.463647609.
463. Okay, that's equal to the inverse tan of x. Now we got something to work with, because what can I now do for sure?
You can subtract, or you can subtract it from pi over 4.
Take the tan of both sides.
Oh, yes.
I take the tan of the left side, and when I take the tan of the right side, I get x. In other words, when you take the tan of the inverse tan, you get that argument, x. And now you can take the tan of 0.463, and it should be pretty close to 5. 0.5, excuse me.
Yes. I got 0.5 exactly.
0.5 exactly. Okay, interesting. That's the way to do it. And I don't see that there's another way to do it. There might be, but you would think Wolfram alpha would show something different if that wasn't the way to do it. Interesting that that is exactly 0.5. Actually, you shouldn't have gotten, oh, you did probably not round it off, huh? In other words, your inverse tan of 1/3, you probably left that to 6 or 7 decimal places, and then you just took the tangent of that?
Yes, sir.
Okay. So I don't know that the answer is exactly 0.5. Might not be.
Okay.
Because we rounded it off. Even if we rounded it off to 6 or 7 decimal places, still shouldn't come out exactly 0.5. We're going to lose a little bit of accuracy by rounding everything off. So I doubt that the answer is exactly 0.5. And if it was, why isn't that just the answer that Wolfram alpha gave? Exactly 0.5. I don't know. If I look on the Wolfram alpha, it actually appears to be slightly less. No, when I put the cursor on it, it did say 0.5. Okay, I guess we can go on to the next one.
Okay.
The next one's same thing. In other words, figure out what the inverse tan of 1 is. We know that's pi over 4. Figure out what the inverse tan of 2 is. That's something you got to look up. Figure out what the inverse tan of 3 is. Add those three numbers together. That's what x is.
Yes.
My question was, is this the same thing as inverse tan of 6? And again, I cannot take the tangent of both sides here and come up with 1 plus 2 plus 3 equals the tan of x. At least I don't think I can do that. Maybe we can. Why don't we come up with what we know to be an answer and then compare it with that other method?
Yes, sir.
So what do we get for x here?
X is pi.
Oh, really?
I added all of them together, and I got 3.141592665.
Oh, that's pi.
Wait, 92. Yes, it's pi. They just rounded it off.
Yeah, for sure. It's got to be pi. I would think any number that starts at 3.1459 is going to end up being exactly pi. Okay, so that again tells me I cannot take, if I were to be able to take the tan of the left side, it does not come out to be 1 plus 2 plus 3, because that would mean this would be true, which means if I'm solving for x, I'm going to take the inverse tan of 6. Look, see what that is on your calculator.
1.405647659.
Not anywhere close. So you definitely cannot do that.
That's right.
In other words, you cannot. Not erase. You cannot distribute. In other words, this is not equal to 1 plus 2.
That's right.
Because it looks like you could. Looks like you could distribute it to that. That's equal to 1. Plus, you could distribute it to that. That's equal to 2. So it seems like it would be equal to 1 plus 2. But we've seen two problems now where it's not, for sure. That's not a process. The distributive property does not work for trig functions and their inverses.
Yes.
That's worth knowing, that the distributive property does not apply. All right, let's go on. I think hold on. We need to, oops, I don't want to close that out yet. Here's what I want. Yeah. Okay, now is all we need is the answers that are inside the unit circle. In other words,
yes.
solve for x over that interval.
Yes.
All right, let's see. I'm looking for ones that are easy that we can do immediately. I tell you what, these are definitely doable. I believe I can do 5 through 9.
Okay.
Let's do 10 because we're going to run out of time here.
Yes.
You can do 5 through 9. I think you just need to experiment with it.
Yes.
Obviously, tan of x over 2 is, you can probably use the half angle formula, or you could even make it sine of x over 2 over cosine of x over 2. And that might produce answers, but you're just going to have to play around with it. It's a lot like verifying trig identities, sometimes you just have to start and hope that you're not on a bad path. Number 10 is a lot easier to do, but you have to know how to do it. So let's just talk about that for a moment. What's in parentheses is what?
That is...
Or number?
That is the number.
Okay. So, if I draw a triangle, oh, hold on, I gotta do this differently. I think I remember how to do this. If I draw, remember, usually these, you just have to draw the right triangle and label hold on a second. Well,
I think we need to use the calculator for this because it's a 3, 4, 5.
Well, I'm not sure that it is.
Oh, wait. Oh.
Well,
yeah, it's not.
That's a way to do it, but it's not necessary to do it that way.
That's
There's
right.
a different way to do this. I just got to think about it for a second. God, I'm at a loss for how I used to do these.
It's just -1, right?
Well, let's see. The cotan of 3 pi over 4 is -1. So I guess we don't need to draw the triangle on this particular one. There's some of these where the only thing you need to do is draw that triangle and label it, come up with its total dimensions, and then you can figure out, oh, I know, it's problems like this. Problems like that, you draw the triangle.
Yeah.
This one, yeah, I know without a calculator that that's -1. And so the inverse sine of -1 is what?
The inverse sine of -1 is 270, so that is 3 pi over 2.
Yep, so that's the answer. And that's the only answer for 10.
Yes.
Now, 12, let's try doing it my other way. And my other way depends on knowing that that angle is theta. That is an angle inside those parentheses. It's not a number, it's an angle. Okay.
Yes.
This way, let me just, maybe that's the angle whose cotangent is 2 over 3 now this is square root of 13, and if I want to know, now hold on, just ignore that leading 2 for a moment, and then we'll go back and try to figure it out. Let's make that a 1.
Okay.
If that was a 1, then I can call this angle theta,
Yes.
which allows me to dimension completely the right triangle, and now I can take the cosine of theta, which has to be 2 over root 13. In other words, I didn't have to solve for theta. Don't have to use the calculator there.
I see.
Okay, and this is the way you want to do these, where you're taking the trig function of an inverse trig function.
Yes.
Now, in other words, you don't need to solve the inside. Now let's see what we can do with that 2. what do we really have here? We have the cosine. So we have the cosine of 2 theta which is equal to cosine squared of theta minus sine squared of theta. What's cosine squared of theta equal to?
So that's going to be 4/13
minus the sine squared of theta
minus 9/13 negative 5/13.
And now we have to do the process where, what's the next step?
That is,
Oh, that's our answer, isn't it?
yeah, that's it.
Minus 5/13 is our answer. There is no next step. I was going to do a next step to try to solve for theta, but we don't have to solve for theta.
That's right.
We're supposed to solve for the cosine of 2 theta. And that we've got an answer. And we should get a ratio. When you take a trig function of an angle, you get a ratio of numbers.
Yes.
Okay. All right, let me erase this and see which one is only going to take 5 minutes here. Let's see, we've done 10 and 12. 11.
Is number 13 more complicated than it looks? Would we have to use a calculator on that one?
You're going to have to use a calculator.
Okay.
Just add the 2 numbers together.
Okay.
I believe.
Same thing with number 14, except it's that and number 12 combined.
I'm trying to figure out if, in other words, if you do 14 the way you did 10, you'd use the calculator to figure out what that angle is, and that angle, and you take the sine of the sum of those 2 angles. But I think we can probably do number 10 same way we did number 12, or not 10. We can do 14 the same way we did 12, I believe. Let's see if we can. Because that's a better way to do it. If you don't have to find that angle. In other words, we did 12 without finding out what the 2 theta was equal to.
Yes.
12, if we let that angle be theta, problem
you might have to,
that I don't have any way of dimensioning the triangle, because the theta is the sum of 2 angles. No, excuse me, it's the sum of 2. Yeah, it is the sum of 2 angles. In other words, what we really have is a theta 1. Let me see if this helps. Plus a theta 2. Okay. And now we've got, all right, this might work. The sine of theta 1 plus theta 2. I'll draw 2 triangles. I'll make that theta 1. That side is 12, that side is 5, that side is 13. I'll make this theta 2. That's 37, that's 12. Who knows what that hypotenuse is? There's a number there. Just for sake of argument, I'm just going to make up a number. Or if you want to give it to me, that's fine. If you can do it quickly on your calculator. Square root of 37 squared plus 12 squared.
Okay.
Yeah, let's get a ballpark number in there. That would.
Oh boy. You want an estimate?
Yeah.
38.8, no, 38.9.
Okay. So now we can use, yes, this will work. Because this is going to use the sine sum and difference. So we're going to get sine of theta 1 cosine of theta 2 plus sine of theta 2 cosine of theta 1. And each of these we can figure out by looking at our triangles. In other words, the sine of theta 1 is 12/13. Cosine of theta 2 is 12 divided by 38.9.
Yes.
Sine of theta 2 is 37 divided by 38.9. Cosine of theta 1 is 5/13. That's four numbers. That'll give you an answer. And this is definitely the way to do it. Even though you needed your calculator, actually you didn't need your calculator. We never had to solve for theta 1 or theta 2.
Yes.
And yet we were still able to come up with a precise answer. Well, I don't know how precise it is, but yeah, it can be totally precise. In other words, what was that the square root of? We can use that.
1,513.
Yeah, so now we're using everything precise. In other words, sine of theta 1 is a precise answer. All four of these things are precise answers based on these two triangles.
Yes.
And you're going to end up with a perfect answer in terms of radicals. In other words, no need to round off anything.
Yes.
You know what I'm saying? In other words, now that we've turned that into square root of 1513, all of these are precise answers in
That's right.
Format.
Because it's not rounded.
No, it's not round. There's no rounding that's been done. So remember that technique, because it's an interesting technique in that you don't need to solve for the angle. Because all you need to do is to recognize that that is some angle theta on number 12. And you can set your triangle up and dimension it based on the fact that the inverse cotan is 2/3.
Yes, sir.
Same thing with 14.
That's right.
The 15, well, I'll let you go here. The way you graph, I'll do it real quick.
Okay.
First of all, the cosecant function looks like this. One full period of the cosecant function sits on top of the sine curve, tops and bottoms of the sine curve.
Yes.
If I want the inverse, I got to rotate it about that line. I got to reflect it, rather, about that line.
Reflect it.
Yeah. And if I reflect that about that line, I'm not good at this, but you can figure out how to do it. Let's see if I use red. See that point. Yeah, thought I was using red.
Okay, so it's gonna look.
Is that a reflection about the blue line that's above it?
Yes.
And then plus, you're going to have this one reflected, which must look something like this.
I think it's going to be facing, it's going to be opening to the right and to the left.
I think you're right. Yeah. Because at 45 degrees, so it's going to look something like this. Now, interestingly enough, those aren't functions.
That's right.
And that's important, which means that we have to restrict the domain on the cosecant function.
Yes.
In the same way that they restrict the domain when they figure out inverse sine. They restrict the domain from minus pi over 2 to plus pi over 2.
Yes.
Then you end up with a true function when you take the inverse function. And we're going to have to do that here. If I draw the other side of this over here, let's see. That's what I want to do. Instead of like I've drawn it. And now we're going to restrict the domain from minus pi over 2 to pi over 2.
Okay.
And so here, let me erase the part that we don't want. And that is going to give us a function.
Yes.
Let me erase that line from that line. Whatever that reflection is, and I believe it would look something like, let's see, if I reflect that, something like that, I believe. And if I reflect this, something like that. And that is a function, passes the vertical line test. And we did, when you do this with sines, you restrict it always from minus pi over 2 to plus pi over 2. I did the same thing with the cosecant. I restricted the domain from minus pi over 2 to plus pi over 2 and only reflected those pieces.
Yes.
I'm not sure I got this reflection right, but
that's
it is relatively close.
Yes, it is.
Okay.
All right.
That was fun. I love trig. The harder,
yes, sir.
More challenging it is, but we did fine here.
Yes, sir.
And I will talk to you next Thursday, and only for an hour next Thursday, right?
Yes, sir.
Sounds good. Talk to you then.
All right. See you then.
Bye-bye.